Hello everyone, welcome back to another GIS mathematics lecture video, and in this lecture video I want to continue our discussion on map projections. Specifically, I want to discuss the categories or types of map projections. And the reason I want to approach it with categories and types is because there are way too many different individual map projections. There's thousands of them. And there's also custom map projections. But the idea is that the vast majority of these map projections, and any that you would decide to make in the future, are typically going to fall within some of these categories or types. And so understanding these is going to go a long way in helping you understand projections. But before we do that, there are two sort of terms that we need to be comfortable with. The first is this idea of what's called a developable surface. And a developable surface is just really a 2D representation of the surface on which we would make the map. Now, the way that I typically describe developable surfaces is to think of them as a piece of paper, right? And the way that we're going to approach these categories of map projections have to do with all of the different ways that we can take that piece of paper and arrange it relative to what we would call a reference globe, which is the next thing we're going to talk about. Right. So developable surface is just basically, you can think of it as a piece of paper. And the point of a map projection category is to sort of separate out all the different ways that we can manipulate that piece of paper so that it interacts with, again, this reference globe to give us something that we can then project our latitude and longitude values onto. Okay, so hopefully that makes sense. So I've said reference globe a couple times. Well, what is the reference globe? Well, the reference globe is just a rescaled version of Earth, or it could be any surface, really. It's the rescaled version of the 3D surface you want to map. Right, and I say rescaled here because if you think about it, right, whenever we make a map, there's always some sort of map scale, right? And that map scale relates how much distance is covered on the map, relates to how much distance would be covered in the real world. So this reference globe is just a scaled down version, right? So if we wanted to make a 1 to 1000 scale map, right, our reference globe would be a 1 to 1000 scaled 3D surface. This would be an actual globe, right, like you're used to seeing in the classroom, right? So the 3D globe is a rescaled 3D version. The developable surface is the 2D representation. So again, the way that I think about this is the developable surface is like a piece of paper, and the reference globe is literally like a globe that you would see in the classroom. And the map projection categories and types are basically all the different ways that we can take that piece of paper and wrap it without tearing, right? We can't tear it, and wrap it such that we would be able to have that developable surface touching or otherwise interacting with the reference globe. And again, there are thousands of different categories and types, but if we talk about sort of the most general cases, that's going to cover most of the specific map projections. Okay. So in addition to this idea of developable surface and reference globe, we need to think about them in terms of there's three sort of properties or three pieces of information about map projections. We need to understand something called class, the class of the map projection. We need to understand something called the case of the map projection. And we need to understand something called the aspect of the map projection. So class, case, and aspect. I'm going to do my best to sort of draw things out so that you can sort of see how these things play out. Whoa. So class. Class is basically the shape. All right, and so you can imagine that there are all kinds of ways that we can wrap a piece of paper, again, without tearing it. Or in other ways, we can make the developable surface interact with the reference globe. But there are really three that we see most commonly. And those three are cylinder, cone or conic, and planar. So I'm going to do my best again to draw the pictures here. So for cylinder, right, what you can imagine here is you can imagine having your globe. So this is going to be our globe here. So let's do the globe in a different color. Let's make things a little spicy here. Right, so this is our globe. Okay. So with the cylinder, what you do is you literally take a piece of paper. You can, again, imagine the developable surface as a piece of paper. Right? We take the developable surface and we literally wrap it around, right, like a cylinder. And we have a point of contact here, right? So basically along the equator in this case, right? Right, this red right here, this is everywhere that this red right here is everywhere that the surface of the reference globe touches the developable surface. Okay? So this red right here, this is the point of contact. So you can imagine, right, if we were to then take and cut, if we were to separate this back out and roll it flat, because this cylinder is a two-dimensional surface, right? You can imagine what you would get, right, if you were to project all the lines of latitude and longitude. What you'd end up getting, right, is something that looks like this, where your lines of latitude and lines of longitude are straight lines. They intersect at 90 degrees. Okay? So when you do a cylinder, you end up with straight lines for your lines of latitude and straight lines for your lines of longitude. Your meridians and parallels are straight, and they intersect at 90 degrees. Let's talk about conic. So conic, right, again, we're going to draw our reference globe here. So our reference globe, this is our reference globe. Right, for conic, what happens is you literally have it, you put a cone around. Right, you can imagine wrapping up the piece of paper kind of like a party hat, right? And you set the party hat on top of the Earth. So now the Earth is going to a party. It's wearing a party hat. And so what happens here, right, is we have our point of contact being up here, right? The point of contact is now up here, right? Because this is the point where the developable surface touches the reference globe. And so now you can imagine if we were to project the lines of latitude and longitude onto this and then unwrap it, right, what you would get would be something where the lines of latitude, right, are going to appear almost like spokes on a wheel, right, emanating from a point, right, and that point would be up here. And then the lines of latitude are going to be sort of emanating in this sort of circular pattern, kind of like this. Right, so you can see now how just changing the shape, right, just changing the shape from a cylinder to a cone had a pretty drastic impact on the way that our map looks, right? This is an even grid. This we now have, it almost looks like what would be the start of a spider web. And we're going to give ourselves a little bit of space here. And let's look and see what the planar case would look like. Right, so the planar case, right, we have our reference globe. But our developable surface now is just a piece, keeping the piece of paper flat and just setting it on the globe. Right, so now our point of contact is a single point right here. So now you can imagine, right, if we were to emanate out the lines of latitude and longitude, right, coming from here, right, that what we would end up with is going to look similar to conic, but it's actually going to be, right, it's actually going to be a circle like this, right, where this point right here was our point of contact. And the lines of longitude are going to radiate out from that, kind of like the spokes on a wheel. Right? And then the lines of latitude are going to run around it like that. So it almost looks like a completed version of conic in a way. So hopefully this makes sense. Cylinder, we wrap a cylinder around it and we get something where the lines of latitude and longitude are parallel to each other and straight. We have conic, where we have the lines of longitude coming out straight but not parallel. And then we have the lines of latitude sort of curving around them. And then we have planar, where the developable surface is kept as a flat 2D plane and simply set on the surface of the Earth, or the surface of the reference globe, I should say. And you can see that it creates this sort of spiderwork pattern. So hopefully that makes sense. In the next video, we'll talk about case. And if you have any questions, please reach out. Thank you.